Okay, this is the report. This is the link for the submission of the report. And here you will find the lecture. Ba't ganun yan pa? Wait lang. So ko na lang yung existing na bukas. Wait lang guys. So this is our first activity. Pasensya na kung mahaba. Ang kwento kasi niyan guys, the subject or the activities that I'm going to share with you is a compressed version of Applied Physics 186 and a bit of Physics 187. So pasensya na kung marami. Result ng 5-year course collapsed into a 4-year course. But anyway, I hope pinili ko na lang yung pinaka-importanting parts ng subject na yon. So ito na sila. No? So the first one is digital image formation enhancement. So the objectives are you are going to mathematically create images and learn how to save image in an appropriate file format, open and capture images using Python or MATLAB, improve the appearance of gray level and color images, and use the back projection technique to transform the histogram on the image to a desired distribution. Now, I wrote this in a very self-explanatory way. This is 14 pages long. It's because parang nagla-lecture na rin ako. So I suggest you read through this activity thoroughly. Sample codes are given, so you can study the codes and follow through. Okay. And then interspersed are activities that you are to do. Like for example, here you are to make synthetic images. And why do you need to make synthetic images? So that we can do accurate experiments with them. Yes, you can do them in Paint, but what if you need to have an accuracy just like this? Like there must be a correspondence of the pixels to the physical image size or physical object size, all right? So here you're going to, in the first part, you're going to create synthetic images that we can use later for experimentation, right? So I want you to read through this. And then the next part teaches you how color images are formed. And essentially it's an overlay of 3 color channels, right? And so here's another code that shows you how to make circles of different colors, red, green, and blue, and overlaying them. As you can see here, this is the result of that code. When you overlay them, the overlay of red and blue channels produce this image, etc., etc. Okay, so essentially what we see in color images is actually an overlay of 3 channels. And in the next part, we talk about image modes. It's very important because the type of image that we need to analyze need not be a true color image. Sometimes binary or grayscale image is enough. And even if it's a colored image, it may be enough that we represent the colors in a few numbers. That's why there's such a thing as indexed images, index color images. Okay, so read through that as well. Now, there are also different image types. Okay, high dimensional. There are high dynamic range image, hyperspectral image, 3D images, and temporal images. And so in this activity, in the next activity, you're going to create your own color image. In this case, you're gonna reconstruct the Olympics logo mathematically. Okay. Then here's an advice how to save images. You don't save the figure, you save or you write them indeed as an image file this way. Okay. Then the next part is image enhancement. Now, image enhancement, you do it either for a human observer or a machine. For example, you have an image, like say this is dark, but actually there are information there. It just looks dark to us, but the camera can actually pick up information. In fact, if you look at the lady here, no, and you boost the grayscale, or rather the values you see, or the brightness, you can see that indeed the dark part here actually contains information. We just don't see it because Our eyes are not too sensitive, but the camera was able to pick up these details. All right. So you enhance image again. You enhance image either for a human observer, like say, this might be an X-ray image. So you want the doctor to see the details. So you can boost this image or enhance this image such that more details will come out on dark parts of the X-ray, for example. So that's a human observer, like a doctor, for example, looking at X-rays. Or you may want, or you may need to enhance the image for a computer. Like, for example, it will go to another stage of processing and the image needs to be enhanced before it goes to that. Otherwise, the next stage will have a problem interpreting the image, okay? And so in this next part, you're taught how to alter the so-called input-output curve of the value of an image. And here we will use the software, GIMP. It's like Photoshop, but free. So it's very powerful. So you can download it, it's freely available. And here are some techniques how you can boost or rather improve a dark looking image to tease out the details that is not very obvious. You can also do that programmatically, meaning through a program, through a technique called histogram manipulation, or in particular by back projection. And this next part teaches you how to do it. Back projection has many uses, and this is just one of them, okay? So knowing this technique, you can actually apply it to many others wherein you have a probability distribution function and you want to map that probability distribution function to another PDF, okay? So this is an useful skill to know. And here, it is illustrated how it's done step by step, okay? So ginawa ko to na parang textbook guys itong discussion dito, so you can read through it carefully, follow it, and then you can do it on your own. Okay, that's why 14 pages siya. Of course, there are sample code as well. So yeah, okay. Then another improvement that you can do or enhancement you can do is contrast stretching. Okay, and for color images, there is white balancing. Okay, has it ever happened to you that you take a picture and even though you know that your t-shirt is white, your t-shirt doesn't look white in the image? Like here, for example, okay, white yung background, pero dahil kinuha ko to under a hall with halogen lamps, nagmukhang yellow, and overall the image is having a yellow cast. So there are white balancing algorithms, and here you can study how they work. Sometimes you see color is an important feature for, say, image processing or pattern recognition. So having the correct color appearing in your image is an important pre-processing step. You can also play around and use these techniques to restore your faded color photographs. Meron ba kayo yung mga color photographs sa bahay na yung printed printed sa photo paper, yung nagmumukhang ibang kulay na? Maybe your parents do. So maybe you could try and see if you can recover the faded colors. Okay. So that's it for this activity. Before we go, all right, so some reference. Before we go, let me just tell you how we capture, how images are captured. So another slide coming up. But before that, do you have any questions about the activity? Again, it is self-contained. It's 13 pages long because it's like I'm lecturing. So I'm giving you the information there and then, and interspersed in between are the activities. May tanong ba tungkol sa activity 1? Waiting for hands to rise. Wala. Going once. Going twice. Ayun. Yes, Linus.
Question po, ma'am. Well, do we have to install any specific add-ons sa MATLAB for this SEM?
Very good question. Yes, image processing. Okay, you look for the image processing toolbox. Oh, by the way, you can also do this MATLAB online. Have you ever tried MATLAB Online. Kasi pag MATLAB Online, nandun na lahat. Sometimes hindi. Like some computer vision apps do not work online. So if you are going to download MATLAB, please make sure that you also install. I'm gonna write it in the chat. Image processing toolbox. Okay. Baka iba na yung pangalan niya. Baka meron kayo makitang computer vision. The toolbox. Okay din niya. Okay. Hindi ko maalala kung ano yung, usually kasi sa online lang ako, pero kaya hindi ko maalala kung ano ba yung pangalan. Basta merong keywords na image processing and computer vision, you're good to go. Good question, Linus. Sige, ano pa? Okay. Kung wala na, another one last slide. Okay? Okay. So pag-usapan lang natin, okay, we are dealing with images dito sa module na to. So it's best to understand how images are formed, digital images, no? So consider cutaway of a color camera. Uy, move. Nag-move ba? Tayo mag-move. Yan, okay. So consider a cutaway of a DLSR. So here's a camera, digital DSLR, digital single lens reflex camera. No? So you have your lens barrel. Okay, here are the optomechanical parts. Here are the lenses, very compound. Viewfinder here, no? And then here are the optoelectronics. Ito banda, ito yung sensor. This is the mirror that folds up if you press the ano may shot, ano ba yung tawag doon? When you click, okay? And so the light coming from this falls onto the sensor. Otherwise, it goes to the viewfinder. No? So nakikita mo sa lens, goes through this mirror, gets reflected to this dome prism, goes to your eye. So when you press the shutter, this folds up and the light lands on the sensor. So what you see is what you get. And then you have your other, so the sensor is like your human eye, no? The retina, and it has photosensitive elements. Of course, the digital electronics are here. You have the analog front end, which takes care of the analog to digital conversion, and of course the timing of the electronics. And there's a digital signal processor built in-house again, so that you can save the images and do some processing within the camera. So let's take a look at the camera sensor in detail. Okay. Now, typically there are two types: the charge coupled device or the complementary metal oxide semiconductor. Ito yung may nagpo-form ng pinaka-pixels natin, guys. Again, it's similar to the retina of the eye, no? So each of these are your picture elements, and these are photosensitive, the most photosensitive parts, and this is formed into an array. Okay, and they convert light falling onto them to electrons, okay, or charges. Okay, so ang kinaiba lang nila is the charge that is generated at the CCD, when it's sent to be converted, moves in a bucket brigade style. Punta siya, pag ganyan siya. Okay. So medyo may katagalan kasi this has to, may konting katagalan kasi this has to be sent in a bucket brigade, and the conversion is done pagdating dito sa part na to. And then of course there's a buffer. Meanwhile, yung CMOS naman, transistors kasi yan eh, dito mismo kino-convert yung photons to charge. Okay? Dito mismo. Which is why ang CMOS sensor ay napakabilis. Mas mabilis siya kaysa CCD. So high-speed cameras usually ito yung gamit-gamit nila. Dahil ito, tatravel pa dito. Whereas sa CMOS, dito na nako-convert yung light to voltage. Okay? So they are the pixels of the cameras. Now, since they are light-sensitive elements, their sensitivity, they have a sensitivity dependence on the wavelength of light. When you talk about the visible wavelength, typically it's from 400 up to 600 plus, sometimes up to 700 ginagawa nila. Imagine niyo tong wavelength of light na to as Roy G. Biv. Red would be here and violet would be a little here. So Roy G. Biv would go this way. Okay? These are in nanometers of wavelength. Okay? EM wavelength. Okay? So this is the visible spectrum. Now, a typical CCD is actually sensitive up to near infrared. So nakaka-detect din siya ng light. The sensitivity here means if you shine light of equal power on the sensor, how much of that is converted? Sometimes it's called, that's why sometimes it's called quantum efficiency, and it's also sometimes it's also called relative spectral response. Okay, so how much of you shine light of uniform power, and how much of that is converted to a sensor output voltage, for example, or charge. Ganito. So itong pula. Okay? So sensitive ang ating mga CCD cameras up to infrared. But ayaw natin yan pag kumukuha tayo ng images dahil magiging masyadong dominant yung infrared light, no? And which is why most commercial cameras with CCDs and CMOS have what is known as an infrared cutoff filter. It's a bandpass filter which will remove this part of the light coming through the sensor, IR cut filter. So essentially, pag tinanggal mo yung IR cut-off filter ng isang camera, like most webcams do that, do have IR cut-off filter, you can convert it easily into an infrared camera. Here is the efficiency of a CMOS camera. Once again, you see that it extends to the near infrared. All right. Okay. And some are sensitive, highly sensitive to ultraviolet even. So it can be even converted into an ultraviolet detector. So essentially, by itself, a monochrome, a CCD or a CMOS sensor is a black and white camera. Okay? So how then do they detect color? In front of the camera array, pixel array, you can put filters matching the pixel location. So in particular, we can put a filter mosaic. Shown here is what is known as a Bayer filter. Color cameras exploit the trichromaticity of human vision. Trichromaticity means we only need 3 colors, 3 lights combined in different proportions, no? Different intensities to reproduce the colors that we see. And so these primary lights would be red, green, and blue. Okay, so if we combine these primary lights in different proportions, we can generate a sensation of a color similar to, we can reproduce the colors. See it, only 3. Only 3 lights in different proportions. You might notice, teka muna, bakit lamang ang green dito? But kumbaga, notice here that one color pixel actually needs 4 pixels on the CCD, because this pixel will get how much blue light goes through, how much of the red light gets reflected of the image, and how much green light. And it seems dalawa yung green. It's because the human eye is highly sensitive to green light. And so, since we are more sensitive to green light, manufacturers of the designers of this filter decided that green light should have more pixel area to capture. Technically, physically, tingin ko dapat baliktad kasi we are actually not so sensitive to blue light. Dapat ang feeling ko dapat mas marami to. But anyway, this is how it's done. This is how it's created, and this is called the Bayer filter mosaic. And so, kailangan lang i-interpolate. para makakuha, kunyari, this is 200 by 200 pixel, eh, one color pixel is, you would need 4 pixels. So parang naging lower resolution, Well, what you do is what you call demosaic it. You interpolate kung ano yung mga colors in between. So you take all the blue assigned pixels, and you interpolate what could be the blue in between these 2 pixels. So you generate a channel for red, green, and blue. Do it for all 3 channels. Okay. They're not the only type of color filter around. No? Meron ding mga manufacturers na ang gamit-gamit ay cyan, magenta, yellow, and green. The minimum is 3, no? Three primary lights, no? But you can go higher. No worries in going higher. In fact, there's another filter mosaic that has clear, no? Clear lang. So lahat pwedeng pumasok. Panchromatic, pwedeng pumasok lahat ng light. And then there's what are known as 3-sensor array cameras. So if you look around, you see them called 3CCD or 3CMOS. Kasi imbis na may filter mosaic, nag-assign na lang sila ng 3 CCD or CMOS na tig-isang filter. Tig-isang filter. So the light goes through prisms that divide the light into each of these sensors. And ang kainaman niyan, no need for interpolation. And because you do not interpolate, the images will appear more crisp, more sharp, just like this in this comparison. Okay? Ito yung ginagawa sa mga satellite cameras. Actually, hindi lang 3 yung channels ng mga satellite cameras. 4, 7, 8, and more, no? Pero ganito rin yung idea. The light coming in the satellite camera will be distributed to as many sensors as was designed. So, ang tawag doon, multispectral camera. Each of these cameras will have a bandpass filter designed to capture a certain property of what is observed on the surface of the Earth. Like for example, chlorophyll. So design sila ng filter na will allow the reflectance or the emittance of chlorophyll, the reflectance of chlorophyll to pass through, etc. Okay. So these filters would have sensitivities that look like this. So the filters themselves would have transmittance. So and together with the camera sensitivity, you multiply that transmittance with the camera sensitivity, you get the spectral sensitivity of the color camera. And you can have a look at different camera models and their sensitivities on these websites. Okay. Okay. And essentially, lastly, when you think about the color that you see, it's actually due to the trinity of color. 3 things are needed to produce color. You have your light source, which emits spectral power distribution, an object, which has a reflectance, and your camera, which we earlier said has spectral sensitivity in each of these channels, red, green, and blue. Okay, so the light source would have all the possible wavelengths coming out of it, but the object, which has a reflectance R of lambda, will absorb some of these wavelengths and will reflect off those that it does not absorb. And that light that it does not absorb, that's called the color signal. And that's the light that reaches your camera. Okay. So this is the light that reaches your camera. It's called the color signal. And actually you can simulate what the color will be, the digital color will be, if you know the spectral sensitivity, the light source, and the reflectance. You just divide it by, as you will read later, the white balancing. You just divide it by the light source emittance and the sensitivity of that channel, of the eye channel. Okay, and here you can actually play around and even render colors if you know the emittance of the light source, reflectance of the object and sensitivity of the camera. Okay. So again, trichromaticity. Any color we observe can be matched by combination of 3 colored lights in different proportion. So if lights are the ones that are mixed, it is called additive color. Lights are mixed, okay? But we also have what is known as subtractive color, wherein there is no light source except for the ambient light, but instead pigments absorb parts of those light. So in this case, it's called subtractive color. We know that, di ba, pag minix natin red, green, and blue pigment, eh wala nang magre-reflect. So what we will get is something looking like brown or black, okay? So because it's subtractive, instead of reflecting light, it absorbs part of the light, depending on its absorbance spectrum. Okay. There. Okay. Here's how you can render color, digital color, once you have calculated it. Notice that, diba, dun sa mga slides, in Google Slides or in PowerPoint, we can draw a box and then we can change the color of the fill of the box, diba? So you can do that, easily do that. Once you've calculated what should be the red, green, and blue value, just go ahead and enter it here, and the actual color will come out. In Google Slides, you draw a rectangle and you want to color it. Well, you have to convert these RGB values to hex, and you can actually do that. There's a link that converts RGB values to hex, and then you enter the hex value, and then you can get the rendered color. Okay. Alternatively, you can actually program this in Python or MATLAB, as you will see in your activity. That's it. Okay, I'll stop share. Okay, I'll post this also in Oble. But do you have any questions about this short lecture about how we get digital images and how color is rendered? All right. Okay, so if there are no more questions, going once, going twice. Okay, none? That's it. So ibig sabihin, you accept the terms in our guidelines and you're committing to answer these, or rather to follow these activities. Okay? Kung wala nang tanong, and then that's it for today. And during Fridays, hindi ako mag-synchronous. Instead, I will be available for tutorial. I do that. So kung may nag-ask sa inyo na, ma'am, how do you do this? I'm having trouble how to program this. I can open the Zoom, and sabihin nyo lang, no? And then kahit tayo lang dalawa, we can go through the activities, and I can tutor you how to go through them if you have difficulties. Okay? I just need at least one to ask, naman pwede bang magpa-tutor? And we can do that during our Friday classes. Okay? Tapos na. Kung wala nang tanong, maraming salamat sa pagdalo. Pakisabi sa mga classmates nyo, this is recorded. This will be also posted in our Oblate. Goodbye.